Balancing chemical reactions. In the last video, we learned about what general characteristics of chemical reactions were, what they were, what we were trying to show before and after, arrow, how we change sentences into chemical formulas, and one important part of that I did neglect is everything before the reaction arrow and everything after have different names. When we refer to the things before the reaction arrow, we refer to them as reactants. And when we refer to the things that are made, the things that exist after the reaction happens, we call those products, things that are produced. Products. That's not quite a U. Whoa, and now the board's not aligned. Products. Now, so hydrogen and oxygen would be our reactants, and water would be our product in this case. So that finishes the last lecture. Now let's go back to this. Let's talk about balancing reactions. If we were to actually visualize what this says right here, we could actually draw a picture of it. Every chemical reaction could be drawn out with atoms. In this representation, our little red ones represent hydrogen atoms, and our blue ones represent oxygen atoms. And so when we say H2, not only do we mean that there's two hydrogens, but the fact that it is a subscript 2 as opposed to any other way tells us that those two hydrogens are connected. Subscripts are used for things that are connected to each other with chemical bonds. So the black line right there that connects the two red hydrogens is a chemical bond, as evidenced by the fact that we have a subscript 2 up there. The oxygen also has a subscript 2, that formula. Anything that's part of one chemical formula will be one connected physical object, as you have down here. There's one chemical formula, oxygen. And water has one chemical formula, so they should all be physically connected with bonds. So what we've said in this sentence, in this chemical reaction sentence, is that this hydrogen and this oxygen turn into water. Now, and that's all good and fine, but if you think about it, we have a bit of a problem. The problem is that if you just kind of look here and count, what that means is we actually have to be able to take this and turn it into this. And that's not possible. That's not possible. Not without leftovers. You got to be careful. Chemical reactions are not allowed to have leftovers, because if they have leftovers, that sort of means that something disappeared, or that something, if you have more at the end than you started with, then somehow something popped into existence. We have to make this product out of these reactants. We have to do that. And so if we kind of brainstorm here, how can we do that? Well, a couple of rules. Remember, we can actually, this reaction here does not tell us how many hydrogens, how many of these double things we can have, actually. If we wanted to, we could start with another one, or 3 or 4 or 5, or however many we need. And so, similarly, we could start with more oxygens if we wanted to, or not. Or we could make more than one water. We're allowed to do that. And that's what we mean when we say we're going to balance. We're going to balance the reaction by making more waters, or using more hydrogens, or more oxygens. So how does that work? Well, we can kind of approach this one just by trial and error. Let's count up the hydrogens before the arrow and after the arrow. And there are two. 2 before the arrow, 2 after the arrow. And in terms of the chemical formula, we could have done that same thing. We didn't need a picture to do that. If we count here, we have 2 hydrogens before the arrow, and we have 2 hydrogens after the arrow. Well, let's keep looking at the chemical formula here. If we look here, there are 2 oxygens before the arrow, and oh my goodness, only 1 oxygen after the arrow. So the chemical formula here suggests that one of these oxygens disappeared. And if we go down and look at the picture, the same thing occurs. We have 2 oxygen atoms here, and we end up with only 1. Well, that's not balanced. This suggests that somehow these 2 things, this all turned into that, which would suggest that one of these oxygens just sort of vanished into thin air, which is not possible. That's not possible at all. Lavoisier showed us that this is not possible. In chemistry, we have Antoine Lavoisier taught us back in the 18th century the law of conservation of mass, which states that matter, or atoms, of course, is where atoms come from. Matter cannot be created or destroyed. Can't be created or destroyed. The upshot of that is these atoms that you start with, they have to exist somewhere when you finish. And these atoms that you start with, they have to exist somewhere when you finish. And they can't just disappear, and they can't just come out of nowhere. So how are we going to do this? Well, I've already sort of answered that a little bit. We're going to balance it. We're going to introduce more reactants or more products until it represents a picture that could happen. You can sort of think of it as Lego blocks. In order for a reaction to be balanced, then it has to be possible to take apart the Lego blocks on the left and make the Lego blocks on the right with no leftovers. And so that's what balancing is. So how are we going to do that? Well, the H's we just already talked about. The H's are already okay. We have 2 H's, and we're going to make 2 H's. And so our problem is the oxygens. And so you might say, well, we can get rid of one of those. Well, that's not allowed, because oxygen is a Hofbrinkel. It has to start with 2, so you're not allowed to do that. So we can't do that. We can't change the formula. You can never, ever change a subscript here. You don't balance by changing subscripts. The subscripts represent what they actually physically are. They're their actual formulas, and you can't change them. But what we can do, like I said earlier, is we can bring in more. So right now, we have 2 oxygens. We need 2 oxygens over here. So what if we say, okay, let's make another water. So there we go. Now we have 2 waters, and there they go. 2 waters. Now we are fine. Now we have 2 oxygens over before the arrow and 2 oxygens after the arrow. And so that's all good and fine, but we've created a different problem. Now we have 1, 2, 3, 4 hydrogens after the arrow, which means that we have a problem over here because we only started with 2. How does 2 turn into 4? It can't. So we need to make more of these before. So now we have 4 hydrogens before, 4 hydrogens after, 2 oxygens before, 2 oxygens after, and that actually does work. And now we have a solution that works. We could take these apart, we could break these bonds, break this bond, stick 2 of these on one oxygen, 2 of them on the other, and we would end up with this picture over here. And so that's how we do it in terms of pictures. So how do we do that in terms of chemical equations? Well, like I said earlier, do not change subscripts. Never, ever, ever change a subscript. The subscripts that we have going in here, the 2, the 2, the 2, the 1, none of those are allowed to change. What we can change are coefficients. We can change coefficients. A coefficient, as we know from algebra, is a number out in front of a variable. So think of the chemical formulas as variables. We can put them out in front. We cannot put them in the middle. We can't put them in or in the middle. We can't stick them in. They got to be out in front of the chemical formula. They got to be whatever the kind of thing is. we can put them out in front of that. And so all we do here is we put a coefficient to show how many times we made H2. Well, H2 was here twice. So we have H2 and H2, so that's 2 H2s. How many oxygens did we have? Well, we had 2, but we've already represented them. How many O2s do we have? Well, we've got 1 O2. So we could write a 1 there, but in chemistry, as you may recall, we don't often write 1s. 1 is usually understood. So we're just going to leave that blank. If you want to write a 1 there, it's okay, but we will usually leave it blank. And how many waters did we make here? Well, we made 2 waters. So that is how we show a chemical reaction balancing. Now we have 2H2 plus O2 makes 2H2O. And if we want to kind of check that without a picture, you might ask, well, how do we don't want to draw a picture every time, so how are we going to do this? Well, what you can do is you can take your coefficient times your subscript, and that tells you how many of those you have. So we have 4 hydrogens before the arrow, and we've got 4 hydrogens after the arrow. So hydrogen is cool. And then if we look at the oxygen, we have a 1, an understood 1 here. 1 times 2 is 2 oxygens, and this 2, it applies to both the hydrogen and the oxygen because they're all part of one formula. It doubles everything in the formula. So 2 times this understood 1 here will be 2 oxygens here, 2 oxygens, 2 oxygens, 4 hydrogens, 4 hydrogens. We're okay. It's balanced.